And we're going to be taking a look at lines in 3 dimensions. Now, I've drawn a 3-dimensional graph in Maple and copied it over into this PowerPoint. Here's a XYZ coordinate system, 3 dimensions, where I put 2 points on there, and I'm going to label these 2 points or give them the coordinates so that you can see what their coordinates are. And I've got them color coded also. Now, if we write the vector from P to Q, that would be PQ with a line over it. That would simply be subtracting the coordinates of Q minus the coordinates of P to give us each of the components of the vector PQ. Now, the line through P and Q, the green line shown here, contains the vector PQ. We're going to label a point on the line R, and R represents any point along that green line, so we'll just give it the coordinates X, Y, and Z. Now, we know that since it's on the green line, the vector from P to R is some multiple of the vector from P to Q. So we'll use T to represent some multiple. Here's the vector from P to R, X minus 2, Y minus 3, Z minus 4. Here's T times the vector from P to Q. That just means multiply each component by T. Since they're equal, then each component must be equal. So we set the components equal to each other. And we have the set of parametric equations for the line. And we want to get efficient at writing the equation of a line. So notice that you have the point 2, 3, 4, and the vector establishing the direction, -3, -1, -1. And so you'll get pretty good at writing the equations of a line. Now, the parametric version of the equation of a line is not unique, so there's many ways of writing that. For example, if we had started with the point Q instead of the point P, we could have written the X with the X coordinate of point Q, and the Y with the Y coordinate of point Q, and the Z with the Z coordinate of point Q, and we'd still have the same line. Now, the other way of expressing the equation of a line in 3 dimensions is to use what's called the symmetric equations. If we solve each of the parametric equations for T and then set them equal to each other, that's called the symmetric equations for the line. Now, for this example, we're going to write the equation, the parametric equation for this line. So we're going to take the 2 and -3, and that'll give us 2 minus 3t for x. We'll do the same thing with the y. That would be -1 plus 1t. And for the z, so see how quick that is? Now in this one, we're going to write an equation for the line segment from P to Q. Now that's just this piece, not the entire line like we've been doing. Now the only difference is, what we'll do on this one is we'll give the parameter t some specific numbers. And so we do the same thing we did before. We take the point P, and then the direction components only this time we specify that t is only going to be from 0 to 1, and that gets us from P to Q. Now in this one I want to explain how to find the distance between a point and a line. There is a formula for that, but hopefully you'll see where the formula comes from. Now when we talk about the distance from a point to a line, we obviously mean the shortest distance, which would be the line segment that's coming from the point and is perpendicular to the line. I've got that labeled D in this problem. And we're going to label the line and the point like this. We're going to pick a point, any point on the line, and use a vector that's along the line and a vector from the point to the point that's off of the line. And again, that can be any point on the line. And so from these two vectors, we want to look to see how we get the distance d. And I'm just using generic quantities here. So the area, we did this in a previous section of this parallelogram, would be the magnitude of the cross product of u and v. Well, that's also, geometrically speaking, the distance d times the length of u. Like length times width in a rectangle. And obviously we can solve for the d simply by dividing both sides by the magnitude of u. So that basically is the formula that we could use for finding the distance from a point to a line in space. Notice again that the vectors have to be created. So you're given the line, either parametric or symmetric, and you need to find a vector in the line, and you need to find the vector from some point in the line up to the point that you're trying to find the distance to. So here's how we use the formula that we just came up with. First off, what we need to do is we need to find a vector on the line. Well, that's easy enough, because notice right here is a vector on the line. We also need to find a point on the line. Now here we can find a point on the line in symmetric form from the top. Notice this is x minus 0. This is y minus 1. And then this is z minus a negative 2. So there's a point on the line. Now we need to find the vector between P and Q, which again we just subtract corresponding components. So with that in hand, we do the cross product, we do the magnitude of that, and divide by the magnitude of u. Now we could simplify this or rationalize the denominator. I'll show you that next on the calculator. So the program that I've created looks like this, and I'm calling the program D for distance, PT stands for point, PT point, and LIN line. So the way it works is the first quantity in parentheses has to be the point that we're trying to find the distance to. The second thing in the parentheses needs to be a point on the line, which we can get from these numbers. And then the third thing needs to be a vector on the line, which we can get from these numbers. So I'm going to use different variables here. In my calculator, what I've done is I've taken the point, negative 231, that we're trying to find the distance to, and I have stored that as P. And again, it doesn't matter what letters you use as long as you have them in the right order. So this is the point. The other thing, which I'm calling Q on my calculator, is the point on the line. And you can see that came from the 0, 1, and -2 in the equation of the line. And then finally, the vector V is the vector that represents the line. In this case, the 2, -3, and 4. And then your calculator takes care of the appropriate calculations, and we come up with the same thing. But notice that our calculator has this habit of changing all radicals where the denominator is rationalized. So that's the same thing as what we got earlier with a rationalized denominator. Here are some interesting observations concerning a plane in 3 dimensions. Now, for the equation of a plane, we're going to start with a point in space. I've labeled this one P. We're going to have a vector coming from P, and then we're going to have the set of all points Q, where the vector from P to Q is perpendicular to the vector N, the one that we were just given to start with. And so the vector N and the point P are what determines the plane. Now we're going to give them a name. We're going to call the point P X naught, Y naught, Z naught, and the vector N, A, B, and C. And notice the equation of the plane comes from the components of the vector ABC times X minus the point, Y minus the Y coordinate of the point, and Z minus the Z coordinate of the point. Well, this is where the equation of the plane comes from. I'll show you all 3 situations, starting with the 3 points. So we're going to take these 3 points and find the equation of the plane through those 3 points. So here's what we will do. We'll start by finding a vector between any 2 of those points. In this situation, I'm using the PQ. Then we find another vector between any 2 of those points, other than the P and the Q. So we could go with the PR or the QR, or vice versa, RP or RQ. I will do the PR. So to find a normal vector, we need the cross product of those 2. Then we need the format of our equation to look like this, with the coefficients on the front of the parentheses, the components of that normal vector. The x0, y0, z0 is any point on in that plane. Starting with point P, we can write this like this. And then we can simplify and reduce that down to standard form. Now, if you used, instead of the P, the point Q or the point R, you should still come out with the same equation at the end. Now we're going to use point P and line L to find the equation of the plane. So the first thing that we need to do is find a vector along the line, and you can see all we have to do is look at these bottom numbers to find that vector. Then we're going to take another point on that line, which we can see from here is a 0, -1, and then positive 2. Then we will find the vector from that point to the point P, or in this case, vice versa. We'll do PQ. And so now we've got two vectors in that plane. We can do the cross product to get the normal vector. And then it becomes just like the previous problem. Only we can use either of our 2 points. We'll choose point P, and I'll go ahead and plug those in and show you that what we come out with here is going to be exactly what we come out with if we had used point Q. And finally, we're going to use these 2 lines in parametric form to find the equation of the plane that contains both of these lines. So, obviously, we can get a vector for this line just by looking at these numbers, 3, 2, and 1. And we can come out with a vector for the second line, again, just by looking at our numbers. So then we'll do the cross product of those 2, and we get our normal vector. Now for a point, we could use this point from line 1, or we could have used this point from line 2. So either one. And here's what it would look like using point P. And then when we simplify that, we get the standard equation.